Imagine you have a bunch of islands, and you want to build bridges between them so that you can travel from any island to any other island. You want to use as little material as possible because bridges cost money. A minimum spanning tree MST is like the cheapest set of bridges that still connects all islands. It is necessary whenever we need to connect many point cities, computer sensors with the least total cost, length, or time. Without an MST, we might waste resources by adding extra or longer connections that are not needed for basic connectivity. Formally, an MST is defined on an undirected weighted graph G equals V, E, where V is the set of vertices, the points we want to connect, and E is the set of edges, possible connections. Each edge E and E has a weight W of E representing cost, distance, or time. The MST problem asks for a subset T of E such that T connects all vertices, that is, V, T is a tree. T contains exactly the size of V-1 edges. The total weight, the sum over E and T of W of E, is minimum among all possible spanning trees. In other words, find the cheapest way to keep the graph fully connected. Kruskal's algorithm builds the minimum spanning tree by sorting all edges from the cheapest to the most expensive and then adding them one by one, but only if they do not create a loop. List every edge and sort them by increasing weight. Start with an empty set T equals empty set. Look at the smallest edge E. If adding E to T would not make a cycle, insert E into T. Repeat step 3 for the next smallest edge, until the size of T equals the number of vertices minus 1. The result T is the minimum spanning tree. To quickly check whether adding an edge creates a cycle, Kruskal's algorithm uses the union find, also called disjoint set data structure. Think of each vertex as a child in a family. Initially, every child is its own family, a separate set. Find tells us which family a child belongs to its set representative. Union merges two families when we connect two children with an edge that does not yet belong to the same family. If two vertices are already in the same family, adding an edge between them would close a loop, so we skip it. The structure supports near constant time operations using path compression, flattening the family tree during find and union. By rank, always attach the smaller tree under the larger one. The correctness of Kruskal's algorithm relies on the cut property. A cut is a way of dividing the vertices into two groups, S and V\S. The cut property says that for any cut, the smallest weight edge that crosses the cut has one endpoint in S, and the other in V\S must belong to some MST. Kruskal's algorithm always chooses the globally smallest edge that does not create a cycle. This edge is exactly the minimum crossing edge for some cut formed by the already chosen edges. By repeatedly applying the cut property, we guarantee that each edge we add is safe, i.e. can appear in an MST. Since we add the number of vertices minus 1 safe edges, the final set is an MST. Let E be the number of edges and V the number of vertices. The dominant cost in Kruskal's algorithm is sorting the edges, which takes big O of E log E time. The union find operations for each edge take almost big O of alpha of V time, where alpha is the inverse Ackermann function, which grows so slowly that it is considered constant for all practical sizes. So the total time complexity is big O of E log E. Space usage includes storing the edge list, big O of E, and the union find structure, big O of V, giving an overall space complexity of big O of V plus E. Consider a graph with 5 cities A, B, C, D, E, and the following bridge costs. A B equals 1, a C equals 3, a D equals 4, BC equals 2, BD equals 5, CD equals 6, DE equals 2, CE equals 4, BE equals 3. First sort, a B1, BC2, DE2, a C3, BE3, a D4, CE4, BD5, CD6. Start with empty T. Add a B, no cycle. Add BC connects B to C, no cycle. Add DE connects D to E, no cycle. Add a C, this would connect A to C, but it is already connected to B and C through a B and BC, so adding a C would make a cycle ABCA, skip it. Add BE connects B to E. B's component of BC joins with DE component, no cycle, so add BE. Now we have edges of B, BC, DE, BE. Total 4 edges, which equals the number of vertices minus 1 equals 4, so we stop. The MSD cost equals 1 plus 2 plus 2 plus 3 equals 8. The resulting tree connects all cities with minimal total bridge cost. When coding Kruskal's algorithm, keep these tips. Use a struct or class for edges that stores u, v, weight, and overload the comparison operator for easy sorting. Implement union find with two arrays parent, and rank apply path compression in find and union by rank in union. If the graph is huge, but sparse sorting edges is still the bottleneck, consider using a fast integer sort radix sort if weights are small integers. Stop early once you have added v-1 edges, no need to examine remaining edges. For readability, separate the sorting step from the main loop and comment each union find call. If the graph is dense and memory is tight, you may want to store edges in a priority queue instead of a full list, though the asymptotic cost remains similar. Prim's algorithm grows the MST from a starting vertex by always adding the cheapest edge that reaches a new vertex, using a priority queue of frontier edges. Kruskal's algorithm, on the other hand, looks at all edges globally and adds the cheapest safe edge each time. Choose Kruskal when the graph is sparse, E is close to V because sorting edges is cheap. You already have the edge list sorted or can sort quickly. You need to handle many separate components, for example a forest, and want to unify them. Choose Prim when the graph is dense, many edges, because Prim's O of E log V with a binary heap can be better than O of E log E, approximately O of E log V squared. You have adjacency lists and want to avoid storing all edges in one big array. You need an online version where edges arrive gradually. Prim can be adapted more easily. In short, Kruskal equals sort first, connect later, Prim equals grow from one node. Kruskal's algorithm is used in many real-world situations where we need a cheap network that connects everything without cycles. Examples include designing a road or railway system that reaches all cities with minimum construction cost, laying out electrical or water pipelines where loops are wasteful, building a minimum cost communication network, fiber optic cables, and satellite links between data centers. Clustering and machine learning, the MSD can help find natural groups by removing the longest edges. Image segmentation, treating pixels as nodes and similarity, as edge weight, and MSD helps separate regions. In each case, Kruskal gives the cheapest set of connections that still keeps the whole system linked.